Now starting. All attendees are in listen-only mode.
Hi folks, John Goff here from the National Weather Service. We're getting ready to get started here in the next couple of minutes. If you guys can hear me, or one of you on your computers, would you give me just a sound check real quick? Is everybody able to hear me okay? You have a little chat window there in your display screen where you can say yes or no. Great, I see a couple of you have already chimed in. You can hear me okay, that's great. My clock says 6:59, so we'll get started in about a minute and a half, and we'll get going. Okay, everybody, let's go ahead and get started. I've got about 7 o'clock. There may be a few others joining us here in the next half an hour. That's fine. They can join in and pipe in as time is available to them. Thanks for joining me tonight for this short presentation on flash flooding, an inside look at the meteorological causes of flash flooding, and a little bit of an inside look at operations at the Weather Service here in Burlington and how we go about issuing flash flood warnings. Just a couple things before we get started here, and I'll just advance the slides along. This is a pretty simple presentation. At the end of the presentation, you'll be able to ask some questions in your little question little bar down there in your tool menu, and I'll be happy to answer a few of those as time permits. After that, I'll also give you an email or a couple emails that you can shoot me a note if I don't answer your question at the end of the presentation, and I'll follow up with you in a couple of days. So let's go ahead and get started, and I'll just move along here slowly. Here's just a few rules. As with any of these webinars, all your phones are muted. If you have too many people on, even though we have a small crowd tonight, sometimes you can get background noise in there. So again, your phones will be muted. It's just going to be me talking to you. All phones, again, muted. We'll answer a few selected questions at the end of the presentation, like I just mentioned. This will be recorded. We're going to put it on our YouTube channel. It'll be on there in about a week. I'll have to close caption it for those hearing impaired, but you'll be able to pull up our website and go to our YouTube channel and review that if you want to share that with other friends or show people the presentation. And again, tonight it'll last about 30 minutes. I've got 25 slides, something like that, to share with you with some graphics here and there. Again, if there's something you don't understand, shoot me a question in the chat bar there at the bottom, and I'll try to answer it at the end, or I'll follow up with you in the email later. Okay, as I begin, I'm just going to show you a couple quick slides of some historic flash flooding that's occurred in our area over the past 20 years. I'm John Goff. I'm a lead meteorologist here at the Weather Service. I've been here since 2000. Got my start in the Weather Service down in North Carolina. I'm a Carolina person originally, born and bred. Also did some time down in Corpus Christi in South Texas, which is getting ready to have quite the weather event down there, getting ready to be impacted by a major hurricane most likely in the next day to 3 days or so. So thinking about some of my friends and coworkers that live down there. Here's some shots of some very historic flash flooding. It remains the biggest weather threat basically to life and property in our region. Flash flooding is a main threat. You can think about all the impacts of lightning and snow and things of that nature. We don't get a lot of tornadoes. Flash flooding is the major threat. This is some flooding that occurred in Barry back in 2007. Some of you may see some of these pictures as familiar. This is some very big flash flooding that happened in the Barry, Stockbridge, and Gainesville, Vermont area. This is some flooding that happened down in the Ripton and Hancock area back in 2009, I believe. This is unrelated to Hurricane Irene. Just some thunderstorm-related flash flooding took out a lot of infrastructure. Luckily, nobody lost their lives on these events. And then finally, once again, this is some shots from, I believe, the Barry area more recently, I think in 2012 maybe, or 13, when one of the creeks there in the Barry area blew out after some torrential rainfall and heavily damaged some areas, including a car dealership, and you can see some of the aftermath of that. And then finally, here's just some rural flash flooding that typically happens every year. A lot of times during these events, culverts would be overwhelmed by the volume rate of flow of the water, and the culverts are overwhelmed, and then the creek flows around the culverts over the roadway. In this case, this is a secondary road, a gravel road, and easily erodes the road surface, making it impassable. Okay, what defines a flash flood as we move on? Basically, it's a rapid onset flood caused by heavy or excessive rainfall in a short period of time, generally less than 6 hours. It's usually caused by torrential thunderstorm rains, but it can be caused by dam failures and mudslides as well. Geological features like a mudslide could come down and block a creek or a river. It can also happen with an ice jam. I don't explicitly mention that as well. Flash flooding can back up rapidly behind a wall of ice and flood, such as in Montpelier in 1992. So that certainly can happen as well. What I'm basically going to cover today is the thunderstorm-induced flash flood, which is by far the most common way of getting flash flooding to occur. So on our discussion topics and overview to here today, we're basically going to cover the ingredients needed to cause flash flooding, how flash flooding evolves, what's called flash flood guidance, and I'll go into that a little bit in a little while. It's a tool that we use as meteorologists to gauge the potential for flash flooding and to gauge how much rainfall will it take to produce flash flooding. Some of the measurement tools and forecaster challenges we face when predicting flash flooding. And finally, a little discussion about the warning process and operations here at the Weather Service and our coordination with our partners. So let's start with the ingredients. What is needed to cause flash flooding? For a storm to produce flash flooding, and these are general definitions, they're not tried and true in every case, but this is a good rule of thumb. It must produce heavy rain over the same area for a period of at least 45 minutes to an hour. Typically, you want heavy rain falling over a particular area in a time frame that's at least 45 minutes to an hour. If it happens less than that, generally, you don't have enough rainfall to accumulate to really produce big-time flash flooding. You generally want to see that in a little bit of a longer time scale. So basically, the little equation that I wrote out there in the bottom, FF, flash flooding, you need heavy rain and what I call residence time, which is mainly another complicated way of saying over the same area. Residence time, how long will that storm reside over the same area? Okay? So moving on, there are many factors considered. So those are the primary things, heavy rain and how long it sits over the same area. But there's a myriad of factors that go into what produces flash flooding, and I've listed just a few here. They include steepness of terrain, or is it falling on a flat cornfield or in a mountain valley? Because the steepness of terrain will allow the water to rush downhill and run off faster than it would be on a flat area. What's the ground type? How absorbent is it? Is it rocky soils that won't absorb water that well, or clay that'll tend to not absorb quite as fast, or is it something like sand where it'll absorb the water really fast, such as the case of Florida, which is mainly a sandy type state, and you can pour a lot of water on Florida and it doesn't flash flood as much because the sand absorbs it a lot. So ground type is very important. How about land use? Is it an urban development land, urbanly developed, or is it a rural area? Because if it's in an urban area like downtown Burlington or New York City, there's a lot of paved surfaces of asphalt, roads, parking lots, etc., and the water won't absorb into those areas quite as quick as it would be in a rural area, which is open soil. So another thing to consider. And then another one to consider is moisture content on top of the soil layer. Is the top a foot or 2 feet of soil, is that very moist, or is it a very dry soil? Often when it's a very dry soil, it'll be able to absorb the water quite quickly. There are exceptions to that, but that's generally the rule, as opposed to a very wet or near saturated soil where the ground does not have the capacity to absorb the water fast enough, and it'll run off quicker. So when we talk about heavy rain and precipitation, the precipitation rates are very critical, and I'm going to go into this a little bit in just a second. I'll give you two examples here. Which is worse, a half an inch of rain in an hour for 3 hours, or 2 inches per hour for 2 hours? Now, of course, if you add those up, the bottom storm has 4 inches of rain and the top storm has 1.5 inches of rain. So that's obviously going to be a pretty easy clue, but I wanted to get the case laid down here to kind of show you a few things in just a minute. course, it's going to be that one, and I'll show you in a minute. So when you get really high precipitation rates, it basically leads to exceeding the soil's infiltration capacity, or the ability to absorb water, when you're really dumping a lot of rain very quickly on the soil. So it exceeds that capacity, and then rapid rainfall runoff occurs. And this little diagram shown on the right there basically shows that. The infiltration excess overland flow, it basically overwhelms how fast it can infiltrate into the ground, and it just starts pouring across the ground surface. So comparing those two storms I just gave you, Storm A and Storm B, basically I've just kind of plotted them on a little simple X and Y axis. So precipitation rate per hour is on the Y axis, the vertical axis, and the time is across the bottom on the X axis. So in the Storm A, you can see the rainfall picks up to quite intense rainfall. So it increases up to an intensity of almost 5 inches an hour there at about 40 minutes into the time period, and then gradually tapers off. Whereas Storm B, your precipitation rates don't even ever reach over 2 inches an hour. So that's one thing that really draws into these storms. And when you compare how much rain they dump over a given area, if any of you have had some algebra or calculus in high school, you basically just integrate under the curve, and you can get a total amount of rainfall that falls. So when you compare these two, Storm A, you get 4.14 inches in 2 hours, Storm B 1.51 inches in 3 hours. Storm A is definitely going to be the more problematic storm because you're dumping a lot more rain in a shorter period of time. So again, heavy rain, residence time, and the intensity of that rainfall. If you have light rain, like in the winter, it can rain for 2 days straight, and it's not going to flash flood because the rates are not that excessive. So again, talking about those residence time, we're talking about how long does the heavy rainfall stay over one particular area, or in this case a watershed, a small creek watershed, things of that nature, over a period of time. So there's several causes of why things, or why thunderstorms or rainfall have long residence times. And I've listed 3 of the major causes here. One are stationary thunderstorms, a thunderstorm that just pops up and doesn't move. You've also got the second example, and I'll go through these examples with you, of training, or what we call back-building thunderstorms. This is basically where one thunderstorm moves over an area, followed by another one, followed by another one in a long train. And that happens quite frequently in these parts of the world and in many areas that have thunderstorms when you have flash flooding events. And finally, a pivoting area of heavy rainfall, especially a large area of rainfall. So let's go into those examples, how the flash flooding evolves. So again, I think that's just a duplicate of the first slide I gave you there, so we'll move on with that. So here's the first example, the isolated stationary thunderstorm. I've basically just done a plot with a kind of a rough schematic drawing I did of what a radar output would look like. Reds and yellows are heavier rainfall, green is lighter rainfall. And the crosshairs on each of these plots at t equals 0, 1, and 2 hours is some particular location and time. In this case, shown by the picture on the right, we have just one thunderstorm and it doesn't move. So if you look at the crosshairs on the chart at 0, 1, and 2 hours, that thunderstorm just sits there and just dumps really heavy rain over that small area. So that's one way you can get flash flooding. The second one is that back building or training thunderstorms. I've show you a radar example there on the right where you see kind of in the middle and right part of the radar image a line of storms that are all kind of stacked up on one another. And that's what I've attempted to show in the diagram at the left here. You start at 0 hours, you have a storm form over the crosshairs there. By 1.5 hours, that storm moves off to another point to the far right of the diagram, and another one pops up in its place. And you can see a third one getting ready to form to the left of that. And by the time you get to 3 hours, there are more storms continuing to move across the area. So these are not the single thunderstorm, it's multiple storms, and they're continuing to move across the same area. So that's the second way you can get it, training or back building thunderstorms. And a final way you can get it is a pivoting area of rainfall, a large thunderstorm complex. Sometimes we call them mesoscale convective clusters, especially out in the Central Plains. You have these large clusters of large thunderstorms that can affect areas, or often it can happen in a tropical cyclone. So it's a very similar thing as you see on the schematic here, and I've got a tropical cyclone image. I believe that is Matthew from last year up the Florida coast, where it's just pivoting as it goes by. And so in the crosshairs, it's moving over time, but it's pivoting at the same time, so that area in the crosshairs stays under the same area and gets very, very heavy rainfall. Okay, let's move on. We've talked about the causes of flash flooding: heavy rain, rainfall intensity over the same area, and some of the causes of it in terms of meteorological causes. We have the single thunderstorm, the training thunderstorms, and the pivoting area of heavy rainfall. Now we're going to move on to a topic called flash flood guidance. As a meteorologist, when I sit down at my desk, excuse me, and I look at a given day and thunderstorms are going to occur, I need to find some sort of guidance or get a picture in my mind of what it's going to take to produce flash flooding on that given day. Because every given day is different, every given area is different, so I have to take a lot of things into account on what I'm basically looking for. It's not an exact science. So we're going to talk a little bit about flash flood guidance and how that works. Flash flood guidance is mainly a product that is issued by one of our river forecast centers, and I'll show you a map here in a minute, that helps me as a meteorologist gauge the approximate rainfall rate to trigger flash flooding. It's output in 1, 3, and 6 hour increments. So basically what that means is, what is it going to take to produce flash flooding in 1 hour? How much rain do I need? Or how much rain do I need in 3 hours to produce flash flooding? Or how much do I need in 6 hours to produce flash flooding? And it's output by county or grid. So it can be for Chittenden County only, or in a smaller grid-based type of graphical forecast. We can also have tables to look at values. So I've shown you a table here, and I've just listed some values that were typically for a given day across our area. And you can see in the table there, it lists some of our New York counties, and you can see St. Lawrence County, Franklin County, Clinton County, and in the columns you see 1, 3, and 6 hours. So if you take the first example, New York Z, New York Zone 26, which is northern St. Lawrence County, on this day it was estimating I need 1.9 inches in 1 hour to produce flash flooding, 2.2 inches in 3 hours, and 2.7 inches in 6 hours. So that's a gauge that I can use to maybe get a picture in my mind. Now, of course, this is going to vary day to day. There's a lot of complex modeling that goes in behind producing this data. If it's a very wet period, those numbers may be lower. It may not take as much. If we've been in a long dry stretch, it may take more. Some of the values may be a little bit lower or higher based off of, is it mountainous or flat, or vice versa. Here's an example of the graphical format that you can output. So this is some graphical output put out for the western high plains in southeastern Colorado for a July period. And you can see the values. The lower values are in southeastern Colorado, the higher, or lower values exactly, and the higher values are in southern Kansas and Oklahoma. Could that be mainly because Kansas and Oklahoma is flatter? Well, that's part of it. Could it be the higher values in Colorado are steeper terrain? Maybe. Or maybe that part has been a lot wetter than the Kansas and Oklahoma portion. So you have to weigh all these factors combined. Again, they're issued by our National Weather Service River Forecast Centers. There's several of them around the country. The Northeast River Forecast Center in Taunton, Massachusetts, which is right outside of Boston, covers most of the Northeast, and we communicate with them daily to get this guidance and to help us out when we're dealing with flash flood potential. This product is issued 4 times daily at 2 and 8 a.m. and 2 p.m. and 8 p.m. And again, the Northeast River Forecast Center is near Boston. You can see several others around the country. Okay. So flash flood guidance, when I get it in, is it good or not? It's just guidance. That's all it is. So you have to use your experience and what you see as the current situation on whether you look at that and say, I believe that, I think that's pretty accurate, or no, I think that's garbage. I think that's not high enough or too low. So you ask, is the guidance good? And based off of what that guidance is and what I've seen, how wet it is, what the potential rainfall is for that day, how much rainfall do I believe that it will cause problems given the current condition? Ultimately, it's going to depend. A myriad of factors. I've been here about 17 years. There's a couple old rules of thumb that I use, not even dealing with the guidance. If I get 3 inches of rain in the mountains within 1 hour, I'm going to have some problems. I just know that it doesn't matter if it's dry or wet. I just know that's going to happen. If it's in the flatlands of Chittenden County or in the St. Lawrence Valley, then it may depend a little bit more. It may take a little bit more rainfall to get that happening. But basically, that's one rule of thumb I use. If I get over 3 inches an hour, I better be paying attention. Outside of that kind of high-end type of thing, again, it depends. So we have many tools to estimate precipitation because we have to know what the ground truth is, right? To know whether I believe what's happening. The radar could be showing a lot of heavy rain, but what does that mean? So we basically use the radar precipitation estimates because our radar can estimate how much precipitation falls in the area, and rain gauges. So the derived precipitation comes from the Weather Service radar and from automatic gauges. There's several different measurement options, and I've listed them here below. One is legacy estimates. The radar has been constantly upgraded over the years. We got the radars back in the 1990s. It's fairly old technology, 1980s technology. So there were some legacy or old-time estimates that the radar still has available to us. And believe it or not, sometimes those can be just as good as even the more modern estimates. So we always have those to fall back on. We have something called dual polarization estimates. Basically, with the more enhanced technology, the radar can see the shape of the raindrops, how round they are, how tall they are, basically how the little raindrop looks in time and shape. So it can theoretically give better estimates, although that's not always the case. Lately, something that we've been using more frequently in the last, I would say, year to 2 years is something called MRMS, or multi-radar, multi-sensor estimates. And this is where the product will estimate what the radar is seeing and combine it with what the gauges are estimating, develop a bias based off of the radar estimates and the gauge estimates, and give a more accurate result. Lately, I've been very impressed by the MRMS estimates, and I've leaned more heavily toward those estimates when in a flash flooding situation. And then finally, we have just the raw gauge estimates. The National Weather Service owned gauges and on our weather instrumentation scattered across the 2-state area are PWS, or private weather stations. Many people across the country have private weather stations that they can upload the data to the internet, and we can pull that in and plot it on a map and see it. And so we can cross-reference what those gauges are saying as well as what the radar is saying and get a picture in our mind what it's looking like. So the radar estimates come in several different sizes. We can get several different ways, shapes, and forms. We can have the instantaneous rates. Remember, I showed you below how critically important it is, how heavy it's falling at every given instant. So we can show you the instantaneous rates that are falling. It can give you 1 and 3 hour running totals, precipitation totals. It can give you a running storm total. And it can also tell you precipitation type, rain or hail. And I say that because that's important when estimating precipitation. When radar detects hail, it can actually indicate from the color coding on the radar that that's really heavy rain. And if you know it's hail, as a meteorologist, you can think in your mind that it may be overestimating the rainfall a little bit if you have large hailstones up in the cloud. So again, differentiating between rain or hail can be very important when assessing how accurate is the rainfall estimates. Here is one of the radar estimates that I worked, an event back in July of this year, late July. We had an extremely heavy rainfall event happen out in western St. Lawrence County. It's kind of hard to see here, but that's the western part of St. Lawrence County with the St. Lawrence River running up on its western extremity there. So that's happening out there toward Chippewa Bay, Hammond, Alexandria Bay, kind of to the north of Watertown, New York. And you can see the estimates there over, this happened over only about a 3 to 4 hour period of up to 6 to 8 inches of rain. And they had some definite flooding there. Luckily, this was a very flat area, so the flooding wasn't severe, but we did have a rain gauge report in that area, which I don't have plotted, that was estimating 7 inches of rain, and it corroborated what the radar was seeing quite well. And by using that gauge and looking what the radar said, I started to believe that the radar was pretty accurate, and I could lean more heavily and have more confidence on what where the warning should be issued at and if I believe flooding was going to happen. So when we talk about gauge estimates, we talk about the Automated Surface Observing System. You may have heard of that before, ASOS. Those are owned by us, and we have many of them around the state here in Burlington, Plattsburgh, Morrisville, St. Johnsbury, Springfield, Vermont, Messina, New York, Saranac Lake, New York. We also have automated weather observing systems across the state. Those are FAA owned, Federal Aviation Administration. We still get that data in, but they maintain them if they go down and things like that. They are the technical repair people. And sites that have AWOSs are Newport Airport, Rutland Southern Vermont Regional Airport, Highgate, Vermont, the Ogdensburg Airport out in New York and St. Lawrence County. We have state-level systems. The New York State Mesonet is sponsored. It's a state-level measurement system owned by the state of New York, and there's several of them scattered across the state. North Hudson, New York is one example. We can get rainfall estimates from those. And then finally, again, the private weather stations, which should not be underestimated. Those are very critical because those fill in all the holes of where the state and federally funded gauges are. We can't fund 10,000 gauges across the area. So all the tens and hundreds of private weather stations are very critical to fill in those gaps where the federally and state-owned gauges can't. So again, I list those all because those are all vitally important. So let's get to the forecaster challenge. As I sit down, and I've touched on these some already, big questions I have. What estimates to believe? Is the radar good? Are those gauges right? Because the gauges can malfunction too. There's many private weather instrumentation and federal weather instrumentation that sometimes they glitch out, and the weather estimates or the rainfall estimates are not that accurate. So what to believe? Do the radar estimates equal the gauge estimates? If so, then that gives me greater confidence, right? Does the precipitation exceed the flash flood guidance in my head, whatever's listed to me from the Northeast River Forecast Center, or whatever number I come up with in my head? Does it exceed that, and so by how much? Is the flash flood guidance reasonable? Or if not, coordinate with the Northeast River Forecast Center. Maybe we can tweak it or adjust it, or maybe it's too short of a time notice. I need to come up with something in my head professionally to what may happen. Critically important, what are the antecedent conditions? Have we been in a very rainy period? That happened back in 2011 and 12, right? Especially when Irene hit. When Irene hit, we were already very wet. So we got 5 to 7 inches of rainfall, 3 to 7 inches of rainfall. That would have still caused a lot of problems, but not nearly as severe if it had happened in a dry situation. When Tropical Storm Floyd came through in 1999, we're actually in a dry period, and there was very similar rainfall patterns with Tropical Storm Floyd and Irene, but Floyd didn't nearly produce the magnitude of flooding Irene did because it was a dry period. And then again, where's the rain falling? Is the rain falling in Grand Isle County, or is it falling over the high peaks of the Adirondacks? Big difference, especially if you have equal storms, right? So as we move toward the end of the presentation here, I want to talk a little bit about issuing the warning and coordinating with the partners, because that's very important too. If nobody hears the message, what does it matter, right? So the warnings are generally issued if my confidence is high. Generally, if I get above 50% confidence or so, it's better to lean on the side of caution. A lot of social engineering studies have shown it's always better to lean on the side of caution. Issue a few too many warnings and don't issue any warnings at all. There's a lot of studies out there on the social realm of things that show that that's a tried and true way to do it. When I issue them, the warnings, they're generally valid for 3 to 6 hours. It covers the heavy rainfall area. In the graphic here, this shows just some counties in southwest Ohio near Dayton, Ohio, and Cincinnati. Excuse me. So you can see in the red there, that's where the flash flood warnings are in the graphic. So it can be for multiple counties, it depends, or it can be for just a small area within a county, depending on how big the rainfall is. And then I'll always include a few calls to action. Turn around, don't drown. That's our big motto with the Weather Service. Most flash flooding deaths generally occur people driving through high water in their vehicles. They think they can go around the flash flooding or go through it, and a lot of times they drive off the road or there's no road left, and people drown in their vehicles. You can distill that even further. I don't have this in the presentation, but the demographics show that most of the people that die in flash flooding are younger males, I think under 45 years old, and in pickups and SUVs. It's kind of crazy. So that would give the kudos to the women out there that maybe make the better decisions. But the point is, we always say turn around, don't drown, because vehicles are the number one cause of deaths in flash flooding. Obey all road closure signs, because a lot of times these flash flooding events happen at night, and you may not know if the roads are washed out. So you come up to some cones or barriers, don't go driving around that. When they had some really heavy rainfall, I believe last October in South Carolina, and that's where I'm originally from, one of my cousins is a police officer down in Columbia, South Carolina, and one of his major challenges were people driving around barricades and getting stuck and them having to rescue them. It was a real pain and really diverted critical resources to trying to help these crazy folks out when they really need to be in other areas of more imminent concern. So obey all road closure signs, and sometimes, again, I'll put that be especially cautious at night because it's hard to tell sometimes when part of a road is washed out. Then I'll issue some follow-up statements as needed over that 3 to 6 hour period, what have you. I do mention the WE alerts, wireless emergency alerts. Most people on most cell phones now, Android and iOS devices, will have the emergency alerts already turned on your phone. You can opt to turn those off. I suggest you don't. And most of you folks have probably seen those pop up on your phone. Excuse me, they can cover anything from weather alerts all the way up to like an Amber Alert when there's a child abduction emergency as well. So those are very critical. Those are important to have turned on. And then finally, we also have critical coordination with our partners. The warnings are relayed to public safety officials and county emergency management via various communications method channels. We have like a chat room capability here at the office where we can have interagency coordination with a lot of these groups shown here at the right. We also have handheld comms radios. Basically, it's a ham radio that we can coordinate through emergency management, either at the state level or the county level in the case of New York. Vermont, as many of you know, does not have county level emergency management. And the briefings, and also a telephone, of course, pick up the phone, right? I mean, that's the bottom line if you can't get through in some of those other methods. We'll also host briefings for potential upcoming flash flood threats done to partners. They're done either hours to sometimes even days in advance, depending on the situation. Irene, that was leading up several days in advance of warning people and getting the message out to our partners that this was going to be a very, very problematic deal and we're going to have some major problems. Whereas a minor flash flood event where you may not be as confident on where it may or may not occur, but it probably will occur in a few places, they may only happen like a day ahead of time. So we do these briefings on a weekly basis or even a daily basis if the threat warrants that. So that's about all I have. I got about 7:30 here on my time. I hope it was somewhat informative to you. I tried to cover that pretty quickly. Of course, I could go in much deeper and make a 2-hour presentation for you folks, but I don't think you folks would have the guts to stick around that long, and I'd probably bore you too much. If any of you have a question, feel free to type it into your little box down there below, and I'd be happy to answer that for you. I think I've got an end slide here that gives you contact information. Yeah, right there. So either of those top 2 email addresses, you can email me a question if it's something you don't understand. That's just a general social network, NOAA.gov email. That's fine. I get those too. Or you can just email me personally. That's my email NOAA address there as an alternative. And again, after I record this and get it all siphoned off and reformatted, I'll close caption it. It'll take a little bit, and I'll get it on our YouTube channel listed there, which is off our website, which I don't have listed. It's just weather.gov/Burlington, and you can view a recorded presentation of this if you want to look at it again or point others or friends to the presentation. All right, so I don't see too many questions. I want to thank you very much for joining me. I appreciate you folks for joining us. And as we're getting into the fall and a lot of the vacation time crunches we have here at the office trying to fill shifts kind of goes away, I do plan on trying to give some more presentations to everybody. I'll try to cover some more winter weather topics and some other things about the NWS in general that may interest some of you folks. So again, I appreciate it very much. I thank you for joining me, and have a good rest of your evening. Have a good night. Bye-bye.